So the last talk of the day is by Dr. Golam Haider and from IFW Dresden, and he will be addressing individual layers in artificial 2D heterostructures.
Thank you very much for the discussion, for the nice introduction. Yeah, it's really nice to be here, and I'd like to take this opportunity to appreciate the opportunity I have given to deliver a little talk on the work I am doing. I have done previously, and currently I am doing in IFW Dresden. So basically, so far we have heard production and plot of heterostructure and how this heterostructure is producing new kind of functionality. But in this talk, I will try to address individual layers in a heterostructure, how this individual layer leads to this kind of property. And so this work is basically done when I was in Czech Republic, working in nanocarbon group led by Dr. Kalbach, and then Otakar Frank and Jana. They are in 3 different universities. They are working together, and I was also a kind of super postdoc there, and I was basically working with those guys to do the work I am representing now. Basically, this is Albert here, who was an expert of scanning electron microscopy, scanning probe microscopy, and then Vaibhav was producing some of the 2D materials we have used to create some sort of heterostructure, and then Javier was doing some sort of simulation which we have used to explain the physical phenomena we have observed. And then currently I am establishing my group at IFW Dresden. Something is wrong. Okay. At IFW Dresden, I am working very closely with Nicola Pocha. Basically, we have the joint lab, and here I am actually focusing more of creating new functionality with twisted 2D materials. Here are the group members we have, and then without extrapolating further, let's go to the talk today. We have heard about these van der Waals materials, which are really good. It can keep the crystallinity even when we go to the monolayer. This is in huge contrast in compared with the bulk materials, because when we thin down the thickness of bulk material, the interface state really dominate the property. But this is not the case of van der Waals materials, and this actually give us an unique advantage to stack them one after other and then create new functionality. And this is really cool, and this also triggers some sort of very advanced application. For example, this 3D integrated circuit, where one can okay, yeah, okay. So what happens, like we can literally stack different 2D materials. I'll make my voice a bit louder so that so we can literally stack different 2D materials, and then we can create 3-dimensionally stacked devices to integrate more devices in a composite circuit. Now one of the classic example of this one is this device where this is a stacked device of in the bottom of it there is a transistor, and then on top of it there is a memory star, and then this literally opens the door to stack more devices on top of each other, and this is really cool. But what happens when you stack 2 different 2D material, they literally start to talk to each other, and then they hybridize one another, which led to different property. So for that reason, it's really important to understand what happens if we really combine 2 different 2D layers, and then if that really opens the door to create new functionality. For example, if we something is so if we really stack 2 different layers, so there is a I don't know, it's not working. Yeah, there is a animation which is not happening. But anyway, if we literally stack 2 different graphene layer and we make a particular twisting angle, then we really change the band alignment. And if we are really lucky enough stake them in a particular angle, which is 1.1 degree, then we end up with a flat band. And and then if we keep increasing the band, twisting angle, then we really end up with having property of graphene. And another example of it is like if we have 2D semiconductor, for example, here MOS2 and WSE2, and if we stake one after other with a particular twisting angle, we actually confine the exciton in Moore pattern, Moore potential, which led to create the Moore exciton, which eventually, which eventually make the exciton very, very sharp. We can start to see this kind of sharp feature if we are really hitting a particular twisting angle. For example, here at twisting angle 2 degree, we don't see this kind of sharp feature, but if we are twisting it at 20 degree, we start to see this sharp excitonic feature. Now, here in this talk, I'll try to focus in this heterostructure to see what happens in this kind of twisting heterostructure. So here basically there are two different layers. So the bottom layer is MOS2, and then the top layer is MOSE2. Now, sorry, the bottom layer is MOS2 and MOSE2, and top layer is MOS2. Now, when we stake these two material one after other, so basically it creates this, you can see this color, it creates this kind of color at the heterostructure. Now, if we measure the property of this heterostructure, we basically see if we measure the Raman spectra, we basically see two different layers laying one after other. And if we measure photoluminescence in this heterostructure where this only blue color, we see that two different layers they're emitting independently. Now, if we anneal the heterostructure a bit, then we start to see the creation of these two different triangles you can see in the middle. And this triangle is actually when this layer is start to talk to each other. Now, if we keep annealing this one for longer time with higher and also with a bit higher temperature, this will increase further, and the whole structure will collapse one after other, and it will create Moore patterns all over the region. Now, if we measure the photoluminescence at this heterostructure region where you see the triangle, you start to see that now the emission intensity of these two independent peaks reduced a lot. So they really, if you see that it is 100 times magnified, so the intensity between these two reduced a lot. And then there is a new peak coming around this energy, which is basically the interlayer emission between these two layers. And this is a signature of the signature that these two layers now start to talk to each other. Now, if we measure Raman spectra at this heterostructure region in the triangle, we start to see that there is a new peak coming for MOSE2, which is naturally forbidden, and this only appears when the layer start to talk to each other. This actually breaks the symmetry of MOSE2, and this makes the symmetry of the layer in C3V, which actually make this transition allowed. This is the reason it comes in the Raman spectrum. So all those things are really nice. We can now characterize, okay, if the two layers are talking to each other or not. By probing this new mode, we can understand that, okay, the two layers are interacting. Also, there is another signature that, okay, these two layers are interacting. Now, if we measure, let's say, this conducting AFM in this kind of heterostructure, we see that the Moore patterns appear in this region. But if we measure AFM there, clearly there is no sign of this appearance of Moore pattern. Now, if we take a close look in this Moore pattern, we can see that this is not really a hexagonal Moore pattern. This is somehow a bit stretched. And this triggers us to think in a way that there must be some strain, and stretching this Moore pattern in one direction means there must be an uniaxial strain present in this material. Now, this strain is also visible in Raman mode. You can see that the E mode of MOS2 is somehow looks like splitted, or it's a bit broadened, let's say. And now, this is also a signature of strain. Now it's really important to understand what kind of strain is there, because that defines a lot of things in the system. Now, if we have this kind of uniaxial strain in the material, there is already some available reference for us to see, like, what will happen if there is an uniaxial strain present in this kind of system. So here there's a MOS2 system, and if you give a uniaxial strain, naturally you will have the shear, you will have the Poisson's ratio, which will which will make some sort of squeezing in the other direction, and that will be reflected in Raman mode. And if we do the polarization dependent Raman, we can clearly see that for a particular polarization, we will pick up one strain, and we will selectively pick up one sort of Raman mode. And then if our polarization is perpendicular to the previous one, then we pick up the other mode. And by probing the polarization dependent Raman measurement, we can quantify what kind of strain is present in this kind of layer, which is very clearly visible here. And because let's say this strain is interestingly, this strain is not influencing A mode, which is where the sulfur atom, let's say, they are moving perpendicular to each other, perpendicular to the layer. So this strain is not influencing much the other layer, other modes. Nevertheless, coming to the point of our discussion. So now, if we do the polarization dependent Raman measurement of the material we have used, so clearly we see that this mode is behaving similarly what we have seen before. Yeah, okay. I need to be faster. This mode is not behaving as before, because you don't really see the dependence of the intensity with the polarization angle. But on the other mode, we can see this very clear. So this led us to think, and this is the angular dependence. It's not really depend too much on the polarization angle. This led us to think of the presence of complex strain in the system, and then we try to theoretically simulate what kind of strain is present there. So now this kind of simulation is not we will not be able to perform by DFT, because the unit cell is very big. So we use molecular dynamics simulation, and let's say when we have the Murray, when we stake two different layers, we create Murray pattern, and the periodicity of the Murray pattern is defined, can be actually calculated by this formula, where D is the parameter, like the lattice parameter of one of the layer, and then this is the mismatch. And by using this, we can actually calculate the periodicity. Now, if there is no interaction present in this two layer, this behaves like the solid line. But if we start to induce some sort of interaction, then we see that very close to the 0 degree, there is a little deviation. And if we now see the position of MO in the position of molybdenum, we see that close to A is stacking. If the angle is 0 degree, the molybdenum is try to move close to the A stacking. And then if we start to add a little angle, then we see that the molybdenum try to migrate a bit complex fashion. For example, in 1 degree, it start to become spiral, and then in 0.5 degree, it is also little bit spiral. Then if you increase more, it becomes like circular. And then if we have even higher angle, then the periodicity is complete, like it becomes stripes at 5 degree. And then if we go beyond 10, there is no signature of MO movement at all. Now, then we also simulated the Raman spectrum for it, and we can clearly see beyond 10 degree, there is no much change in the Raman mode, but before 10 degree, we can see that the Raman is splitting, and obviously now the migration of Raman, molybdenum is actually the reflection of a strain, because the Raman mode where molybdenum is involved, that Raman mode is shifting. So this is actually translated to the strain. So this strain is now this kind of complex. It's not uniaxial strain. And so this is now clear. Now the question is, can we do this kind of treatment to a layer where the same kind of previously I talked about heterobilayer. Now, if we have homobilayer, can we do this kind of treatment? The answer is yes, but we need to have, let's say, for example, isotopically marked layer. So in this case, we prepared isotopically marked 2D materials. We chemically synthesize MOS2 of pure sulfur 32, pure sulfur 34, and with the different composition of it. And then we see the Raman mode. We can see that there is a clear dependence based on the isotope mass on the system. And here is a plot, let's say when we probe the Raman mode of E mode, where molybdenum is involved, we can see less dependence on isotope mass because the effective mass is less dependent on isotope. But here, only sulfur is involved in this vibrational mode, so we can see that more dependence on isotope mass. Now we have created a heterostructure out of this kind of system, and we can clearly see that the spectrum is, the Raman modes are clearly moving, and this is a work under progress, and we really have very nice result. I hope it will come, it will be available in literature very soon. Now, coming to another point where the interaction, I was talking about the interaction between these two layers, which is like, where we need to give some external influence to create this kind of structure. I want to address this kind of issue at IFW Dresden. So basically, we want to design a system where we can avoid the formation of this kind of layer. So here is one of the system I have designed already in Czech Republic that we have created an ultra-high vacuum system where we can exfoliate 2D layer and then stack one after other at ultra-high vacuum. The real system looks like this. So basically the idea is we completely mimic the movement of our hand in ultra-high vacuum. So we have different manipulators that the manipulators exfoliate the 2D layer and stack one after other. So basically this is the ultra-high vacuum system where we can probe where we can actually observe the manipulation by an optical microscope, and together with it we also have a Raman microscope so that we can also see the layer under ultra-high vacuum. And then here, this is a load lock, and also there is a sample storage so that we can, manipulate many different samples together. Also, we do have a thermal evaporator inside, and this thermal evaporator is basically, to make a large area exfoliation. And then we also have some sputtering, let's say, photoplasma, so that we can have freshly prepared sample, freshly prepared surface where we can do the exfoliation. Nevertheless, we would like to have, here, this is one of the results we do have. So we can clearly see that so big area of monolayer we can produce in this kind of system. And if we use, let's say, silver, we can literally create, a monolayer of, of the size of bulk 2D materials. And you can see in this is in a larger zooming scale, you cannot really see a crack inside. And this is a lead pattern where the spot size of lead is like 1 centimeter. And even in 1 centimeter, we can see clearly, sharp spot, even in monolayer. So this is really cool result. And now the question is, this is on top of metal. Can we now get rid of metal? Yes, we can do that. We need to, create this kind of, metal stripe and then exfoliate on top of that. This is what I already have done. Now the next motivation is to get the second version of this kind of system at IFW Dresden, which we are doing, and with Nicola, and we'll now extrapolate this kind of exfoliation to many different composite materials. And yeah, that's all of the thing I want to talk about. And here is a summary, and I think this is I'll just skip it because we just probed some sort of a strain, and then we have shown the way to produce large area 2D materials. That's it. So it's not basically Raman intensity. Computing means the simulation, the molecular dynamic simulation. We are mostly focusing on peak position, not the intensity there. So no.
Okay. Yeah, sure.
When you say you do molecular dynamic simulation, do you use a model potential, and what kind of potential do you use?
Okay, first of all, this is done by one of my colleagues, but to answer your question, we have this Lennard-Jones potential, which is modified by another potential, I forgot the name. So this is a modified Lennard-Jones potential. That potential was used to integrate the interaction between these two layers, the van der Waals interaction. So it is not completely the Lennard-Jones potential to understand the strain.
But it's a pairwise potential?
No. There is something called CT, and I forgot the name of that.
Okay, thanks.
Yeah. So.
Okay, yeah. You have to shout.
So how I conclude this is the monolayer. So there are many reasons. If we have, let's say, if we have, for example, molybdenum disulfide or selenide, you just measure photoluminescence, you see very strong peak. That is one of the sign of having monolayer. And then the second thing is you can obviously measure AFM, and that's very clear that in AFM you will see it. Okay, so in normal exfoliation, there is no way to control. You just exfoliate to get monolayer, and you keep doing it until you get it. And then in ultra-high vacuum system, the way we exfoliate, we create monolayer, like it will be monolayer for sure. And there is a reason behind that. The reason is basically the assistance of metal. That is like this, there is a kind of interaction, and that interaction is a mixed van der Waals plus electrostatic interaction, and that interaction is highly sensitive to only one layer of the material, and which creates the sensitivity to exfoliate only one layer, not the next one. I do have a backup slide for it, I think. Yeah, this one, where, let's say, forget about this one. So there is a complex strain produced if we want to exfoliate this kind of layer on metal. And this complex strain is actually work against the van der Waals force between the layer in a bulk system. So once we attach the layer on top of a metal, then this complex strain plus the electrostatic interaction between this layer and the metal overcome the van der Waals force between the other layer. So this triggered the cleaving of only one layer, and then the other layers goes with the tape. So eventually you have only one layer on the system.
Gold, but is there a reason?
Okay, the reason for gold is very stable. You can do it in atmosphere.
So
and
metal as such has to be very benign.
Well, if you use silver in controlled atmosphere, you will get it. But in atmosphere, you will not get it because silver will oxidize very fast. And then similarly, if you use, let's say, copper, if you use copper, this oxidizes even faster. Then there is no question of doing this in atmosphere. You need to do this in controlled atmosphere, in ultra-high vacuum or in globe box or whatever. So you need to have your metal evaporation system in UHV system or in globe box.
The
and
work function of the metal does not, for example, platinum is also.
Okay, so definitely there is a role, but I was telling about this electrostatic interaction, right? So that work function really matters. Then there is another parameter which is the, let's say, which is the strain. And if this strain depends on lattice parameter. So that means it depends on the metal, choice of metal. Lattice parameter will change. Yeah.
Okay, if there's, yeah, sure, last question.
No, it's just MD, just molecular dynamics. Yeah. Okay.
All right. Oh, yeah. Anyone online has any question, then please unmute and ask. All right, there seems to be no other question. I would like to thank both the speakers.
Yeah.
And with that,